Now we're going to get into the nitty-gritty of what this statistics is really about. So we did averages, we talked about frequency polygons, we talked about calculated standard deviation, we talked about normal distribution. Well, now we're going to talk about Z-scores, which really pulls it all together again. Just like our normal distribution, talking about that frequency polygons, that brings that in. Well, Z-score is going to take it a step further into the specifics. So as a discussion, we're going to talk about Chris playing in a high school jazz band. Now, I am absolutely paying homage to my band teacher in high school, Chris Jacklin. Absolutely awesome guy. I would take an entire video to explain how awesome he actually is. But we'll say Chris plays in his high school jazz band. Now, band players practice an average of 16.5 hours per week with a standard deviation of 4.2. Now, if you're actually in band, you should make sure that you are practicing. Is just using your practice time in your class is not going to be as beneficial as actually doing your own practicing, does ear training, and properly learning your syncopations and everything like that. Chris practices an average of 22 hours per week. How might you estimate the percent of the band that on average practices a greater number of hours than Chris? So what that means is we're going to create a normal curve for this. We can identify a few key characteristics. Set the floor. One standard deviation, 2 standard deviations, 3 and less. I know that this is not perfect, but allows us to still have a good enough understanding of this. So it says the band members on average practice 16.5 hours per week. So that'd be 34%. That would be less than this. So 16.5 minus 4.2 should be 12.3, 8.1, 3.9. We have 13.5% in this range, 2.35% in there, and 0.15% being less than that. So again, these should be how it should be. We at the same time would have 34% here. We'd have 13.5% here, 2.35% here, and 0.15 right there. So 4.2 above this would be 20.7. This would be 24.9 and 29.1. Now it says that Chris practices an average of 22 hours per week. Well, 22 puts us in about right there. So we know that at least 2.5%, but we don't necessarily know exactly how much percent is in this range. We could do, if we had it drawn perfectly, we could do some split, cut it into specifically 13.5 equal pieces, but that's going to take a long time. It's going to be a long time to calculate exact amount. So what has been developed is a Z-score. So a Z-score is a standardized value that indicates the number of standard deviations of data value that are above or below the mean. So meaning we can calculate what the Z-score of 22 is by using this formula. So Z is obviously our Z-score. X is the data point. So in this case, it'd be 22. Mu is our mean, which is 16.5. And our standard deviation is 4.2. So what that means is this is one standard deviation. This is two standard deviations. Well, obviously, this will come out as a 1 point something standard deviation. We don't know exactly how much it is until we use our Z-score calculation. And specifically, 22 subtracting the 16.5 is 5.5 divided by 4.2 is 1.31. Now you do always have to go to two decimal places. So this would actually be 1.31 standard deviations above. So 22 should really be a little bit closer. Probably about there or so. But still, we don't know that exact percentage. This allows us to calculate exactly what percentage it would be. And we do that by using the Z-score table. So a Z-score table is a table that's used to calculate how many percent of data would be below a certain value that has been calculated. So our value of 1.31 will help us to calculate how much percent would be below 1.31. Our Z-score tables are actually going to be on the next 2 pages here. This first table talks about our negatives. So if you had a Z-score of negative 2.3, we'd line up everything. Negative 2.53, we'd be lined up. How's that number? Of course, the number that we used or calculated here for Chris is 1.31. Oh, that's negatives. So positives. So we always are going to start on the left-hand side, and then we go to the next decimal point on the right-hand side, or on the top. So 1.31, 1.3, 1, line it up. This percentage, of course, yes, it is as a decimal. 1.31 would tell us how much percent would be below. So this would be 90.49%. Would be below. Obviously, then we could quickly calculate how much would be above. Well, how much is above? Just by taking 100, subtracting our 90.49, and we get 9.51%, which includes this 2.5% and another 7.01%. And that's what we're going to do. We're going to do some examples that talk about all that. So in example 1, a company produces bungee cords. The mean of the cords is 75.2 centimeters and has a standard deviation of 1.3 centimeters. Cords are rejected if they're any shorter than 42.0 centimeters or longer than 48% or 48. So if we do it as a bell curve, the mean is 45.2. Each individual section after that is 1.3 higher or lower. So 46.5, 47.8, 49.1. So this longer than 48 is just above that 47.8. Same time, 42.0. Let's see, we're looking at 43.9, 42.6, 41.3. So shorter than 42 would put it about right there. So we're looking at, in this question, we want to know what percent of cords are rejected. Well, it would be anything that would be below there, anything that would be above there. The biggest thing about the Z-score is it only calculates what is below it. So In this case, one of them can be calculated really nicely. This other one, again, it still calculates whatever is below it. So no matter what, because it doesn't lie perfectly on that section, we're going to have to calculate what the z-scores are. So the z-score for the 42 centimeter bungee cord we'll be taking the 42, subtracting 45.2, and dividing by the 1.3. That comes out as a z-score, 45.2 divided by 1.3. Again, go only to 2 decimal places. Will be negative 2.46. Negative 2.46 means that we're going to have to go to the negative z-score table. So negative 2.46 puts us right there. Oh, sorry, wrong page. So 0.0069, which obviously as a percent will be 0.69%. The z-score for the 48 centimeters by quick calculation is 2.15. So we'd have to look at the positive 2.15 z-score table. So positive 2.1, okay, where is the 0.5? Negative 2.15 is this one, 0.9842. 0.9842. Now, obviously, again, that percentage calculates only what is below. So in order to find out what is above that, we'd have to take either 1 or 100 and subtract that 98%. So that one comes out 9842, 0.0158. So what percent of cores would be rejected? Well, 0.69, adding the 1.58%. Forgot the 6. There'd be approximately 2.27% of chords actually rejected. So to finish off our question, is if 20,000 chords are made in a day, how many chords would be rejected? Well, that's a quick grade 8 calculation. Take our 2.27% as a decimal and multiply by 20,000. That's enough zeros. And that one works out. That's exactly 454 chords. And that's our idea behind z-scores. So let's do some more examples. A manufacturer of video games offers warranty. The average span of the games is 32.4 months with a standard deviation of 6.3 months. If you want to only offer repairs to less than 1.5%, what length should the warranty cover? So here's a question where we have a percent, but we're actually going to have to calculate what the z-score is. So you only want to offer repairs for less than 1.5%. So if I draw a curve, we have an average of 32.4. What we need to do is we need to make sure that everything lasts long we only want to make sure it lasts long enough so that only 1.5%, so whatever value this is, let's find out what value would this be so that you'd only have to repair 1.5%. Because if it has a standard deviation of 6.3, if we take the 32.4 and we subtract the 6.3, if you offer a warranty for, 26.1 months, which means that anything that lasts longer than or less than 26.1, you'd have to repair. So the, what does it come out as? 68 and the 13.5 and the 2.35 and the 0.15, you'd have to repair 84% of things. So we want to find out what value do you want to offer a warranty for that you only have to repair 1.5%. Well, that means we're going to calculate what X is. We don't know what X is, but we do know almost everything else. So again, our formula is X subtracting mu over our standard deviation. Our mu is 32.4. Our standard deviation is 6.3. But what is our Z? Our Z is not 1.5. Again, I'll just put that in. We have to find where is 1.5% as a Z-score. (1.5%) equals a Z-score, of, well, let's find out. So first off, that would be 0.015. So where is 0.015 in here? As 0.01. Well, we keep on going down this way, which is actually getting closer to 0, right? Oh, sorry, this is going this way is actually getting smaller. Let's see, 0.015. We have 0.014 almost. So it's going to have to be somewhere in here. Right here, 0.015 is a Z-score of negative 2.17. Negative 2.17. So that's what we're going to put in here. And we're going to have to manipulate and solve for what X is, which means simple manipulation, multiply both sides by the 6.3. Get negative 13.671 would equal our X. Subtracting 32.4. Add the 32.4. And we have X equal to 18.729 ounces. So if you want to repair less than 1.5% of your video games, you'd want to offer something that would be approximately 8.7 months or less. Or 1.5 years. Because that would put it even less than there, which means that you'd be repairing even less than 1.5%. Of course, if you're going to be going into manufacturing like that, you'd also have to make sure that your manufacturing tolerances are up to snuff as well. Alrighty. Next example. You've run a race in 2 different locations. Using the data below, compare the 2 races using your Z-scores. So in location of Vancouver, the running club mean is 25.75. Your run was less than that. It's 25.45. In Lake Louise, same run took you, or the mean is 25.52. But your run was even less than that. So let's take a look at what the Z-scores for each would be. So again, calculation, x subtracting mu over standard deviation. So your run is considered x, 25.45. Subtracting mu, 25.75. All over our standard deviation of 0.62. In Lake Louise, we can do the same calculation, just with the appropriate numbers. All right. So 25.45, subtracting the 25.75, dividing by the 0.62. So negative 0.48 as a Z-score. On this one, 24.77, subtracting the 25.52, dividing by the 0.6, it's negative 1.25. So in each case, now obviously you can see that, yeah, the Lake Louise, you ran much less, with much less time, or I'm assuming it's a time. It's probably a 5K. So we can see from these numbers, negative 0.48 and negative 1.25 means this negative 1.25, you are much below the average. So our mu, negative 1.25 is there. Whereas your negative 0.48 will probably put you only about right there. If we go to the percentages, negative 0.48, negative 0.48 is 31.56. Negative 1.25 negative 1.25 is 10.56. So that means that 31.56% of people would have been able to run in a slower time. Sorry, even faster time, sorry. Because the Z-score calculates how much is below. So to run it very fast, say if we ran it in 29, oh, sorry, faster, sorry, 20. You'd have a Z-score of negative 9.27, which means that you'd be able to go much faster. This one just means that you have run it faster compared to the average person. Especially if you compare it to this one. A couple more examples. So I made mention of IQ scores when we talked about normal distribution. Now we're going to actually do an example of it. So as I had said, the mean was for humans and really anything is set at 100, has a standard deviation of 15. Now, if a person scores 119, how does this score compare to the scores of the general population? So let's find out what the Z-score for 119 and what would it be? So let's see. I get 1.27 as a Z-score. So if we go to 1.27 on the Z-score table, right? 1.27, 89.8. Oh, on page. So 89.8% of people would score below this person, which means technically, and by intelligence quotient, this person is more intelligent than almost 90% of people. What percent of people would have a higher IQ? Well, that's a quick calculation by taking it and subtracting from 100, which works out as 10.2%. What about asking what percent of people would have an IQ between 75 and 115? So I'm just going to, again, draw back to our normal curve. So saying that our average is 100. Now the beautiful thing is 115 sets right at one positive standard deviation. 75, though, does not. 75 is about right there. So this is a -2 standard deviations. Oh, let me change the color just so it's not confusing. This one is -1 point something standard deviations. We're going to have to calculate what it is. At the same time, I'm going to draw back exactly to these percentages as well. So this 34, this total of 13.5, and that 2.35 as well. And then the one, obviously the 0.15 as well. Now, just to confirm, so a Z-score for 75. 75 subtracting 100. So 75 subtract 100 is -25. Divided by 15 is -1.67. Oh, not percent, sorry. That's a Z-score. We have to use our Z-score table to calculate what percent would be below that. So -1.67, -1.67 will be 4.75%. 4.75%. Again, and Z-scores only calculate what is below. And that actually works out nicely because if we're right there, that's 2.5%. Obviously, that means that the other 2.25% is what's left in there. Now, us knowing the fact that this 115 is one standard deviation, we're just going to do a quick calculation just to confirm it. Yeah, it is 1.00. So a positive 1.00, 1.00, 84.13%. Not get confused. 84.13% again is below that. So just want to confirm that. 84.13. Yeah. All right. So if we want to find out how many people would have an IQ between 75 and 115, well, if below this is at 84.13%, and below here is the 4.75%, we're asking, what is this? Quick, easy calculation, because we're just going to find the difference between them. We're going to subtract them. We know that this entire thing is 84.13. This part is 4.75. We just have to subtract it. So 79.38% of people would have an IQ between 75 and 115. I haven't said it yet, but intelligence quotient does not mean how smart you are. Intelligence quotient just basically means kind of in relation to different standards. You can still be smart in different things. It just may not be math and may not be English. My English IQ, probably not the greatest. Math IQ, probably a little bit higher. So I did make a mention that I was going to refer back to these percentages. So between this average here and here, well, let's look at it. 1.00. 1.00 is 84.13. Actually, we can just do it right here. So if this is one standard deviation, and this is the 84.13, this average here would be 50. Well, how much is in between 84.13 and 50? 34.13%, which looks eerily similar to our normal distribution. These percentages absolutely are approximates, but they're good approximates for a normal distribution. That's why I do say that you have to have these numbers remembered. You do have to remember these numbers. Same time remembering the 68, 95, and 99.7. Each of those numbers can actually be calculated further. For example, for the two 97.72, if we were to subtract the 84.13, say 97.72, subtract the 84.13, it's 13.59, which is very close to that 13.5%, which is in that second standard deviation range. If we're talking about normal distribution, absolutely, I want you using these percentages. If you don't have these percentages memorized, there's another way of calculating it. I always give ZScore tables on tests. All right. So running shoes do lose their shock absorption after a mean distance of 640 kilometers with a standard deviation of 160. Most people, they do a rule of thumb that they should replace their shoes after approximately 500 kilometers. That's usually very avid runners, or when the sole of your shoe is too worn out. All right, so you replace your shoes when only 25% of people replace their shoes. What distance do you replace them at? Well, let's find out. Again, using our formula, we're going to find out how long, what distance do you replace your shoes? So we need to find out, what does 25% mean on our Z-score table? What is 25% as a Z-score? Well, let's look for 25%. See, these are point, so that's 2 points here. 25%. See, there's 27%. If we keep on going, see, there's the 20s, there's a 24 point, oh, right here. Okay. So here's 25.14 and there's 24.83. Well, which number is closer? This is 0.14% above it, and this is 0.17 below it. Really, these percentages are so close to each other, what we can do is we can actually just split the difference and say we're going to be halfway in between it. So halfway in between these two values puts us as negative 0.6. Let's see. This should be the 7 column. This should be the 8 column. But let's just double check. Yep, 7 column, 8 column. Which means that we would be at negative 0.675. That is halfway in between negative 0.68 and negative 0.67. So that's what we're going to use as our Z-score, negative 0.675. Our X, our average, 640, standard deviation of 160. Do our manipulation. So negative 0.675 multiplied by the 160. It's negative 108. Calculate for X by adding 640. So you would replace your shoes after 532 kilometers. That means you're gonna have some fun.